Alrighty guys, welcome to a step-by-step analysis of dynamics problem 4b4. So here it is in your textbook here. So what we're given is we have block C has a weight of mg, is traveling with a speed of VO when it strikes a fixed wall. A spring of stiffness K is attached to the front of the block. The spring eventually contacts the wall, resulting in a maximum spring compression of delta max. So using this, we need to find the stiffness of K spring. Here are given values that we're given. So we're given mg, which is essentially our weight force here on block C going down. That's going to be 3,200 pounds. We have our initial velocity VO at 10 feet per second. And then we also have our delta max, which is going to act as our delta x here for the spring at 6 inches. So what we're going to do is we're going to follow the step-by-step process here to figure out this problem. So first step obviously is to draw a free body diagram of the masses in the problem. We only have one mass, which is mass C. So when you draw your forces here on mass C here, we have the weight force, which is that mg. Then we have normal, which always counteracts the weight force in the positive j direction. And then you have your force of spring when you do make contact, which is going to be pushing back at C, essentially slowing it down from this velocity here. So that spring force is going to be found using this formula. It's going to be your spring constant times your delta x. Then step 2 for the problem is to set up your coordinate system. So I just drew it up here, kind of the standard coordinate system with in the right direction will be positive I, and then up will be positive j. So now for step 3 here, you're going to write your forces in vector form. So going back, we have our three forces. We have our weight force, our normal force, and the spring force. So the spring force is just going to be that it's going to be a negative I direction since it's pushing back at it, or just counteracting the positive I direction in the coordinate system there. So you could write it out as either just spring force here, or you can do K delta X. Either way is fine. For your weight force, it is going down on the mass. So it's going to be in the negative j direction, and that's just found by your mg. And then you have your normal force, which is just going to be in the positive j direction. So then step 4 here, so you write your accelerations in vector form. Since mass C is only going in the I direction, we only need an acceleration in the I direction. And I just took it as if it is going from its initial speed to rest, which is what we're trying to find. So I have it in the negative I direction here. And so with this, then you assemble your force equals mass times acceleration equations, and then you separate the parts. So we have the big equation right here is going to be your force of the spring plus your weight force plus your normal force is going to equal your mass times your acceleration C. Splitting it out into its I and j components, you have your negative force of the spring in I plus your negative mg in the j plus your normal force in the j is going to equal your mass times your negative, there shouldn't be a vector there, so that's my bad, your negative acceleration in the C in the I direction, or acceleration of C in the I direction. And so then splitting the parts into I and j, you have your force of the spring is going to equal your mass times your acceleration of C. And then in the j direction here, you'll have your negative mg is essentially going to be equal to negative n. So this is just showing that your normal force is going to be your weight force, is all that that one is showing. So I guess the one to look at will be this one. However, the problem doesn't ask for anything. We can, if we needed to find the acceleration of C due to the spring, then we would use this equation. But for the problem at hand, we don't necessarily need anything from this equation. But it's always good to just write out everything to understand what is going on in your problem. So now we're going to look at the work energy stuff by writing out the tables for the masses for kinetic energy, potential energy, and the work done by non-conservative forces. So first looking at the kinetic energy table, going back to the equation here, obviously this mass is just moving in one direction initially, and then to find delta x max, or when we find delta x max, that's assuming that our mass is not moving at all. So that is the most compression it could have in order to stop that mass from moving. One more. So we're only going to have an initial kinetic energy, which is going to be found using 1/2 times your mass times your velocity squared. So 1/2 m of c and then VO squared. And then obviously it's coming to rest, so your final kinetic energy, or your second kinetic energy, is going to equal 0. For potential energy, it doesn't have, the mass itself doesn't have any potential energy. However, when we are compressing the spring, that is going to create some potential energy. So that's going to be found using our spring potential energy equation, which is going to be 1/2 k delta x squared, and in this case our delta x is going to be delta max. And then for the last step here, for your work done by non-conservative forces, we don't have any non-conservative forces, there's no friction, so that is just going to be 0. So to compile everything together, to assemble our work energy equation, our work energy equation is your initial kinetic energy plus your initial potential energy plus your work done by non-conservative forces is going to equal your final kinetic energy plus your final potential energy. And then writing that out, so we have our initial kinetic energy, which is going to be that 1/2 m of our mass c, VO squared, plus 0 for initial potential energy, plus 0 for our work done by non-conservative forces, is going to equal our 0 for our final kinetic energy, plus our 1/2 k delta max squared for our potential energy. So this is just kind of a note here that we don't really need anything from step 5, so we'll only be using stuff here from step 9. And then these are just our givens rewritten again. So in order to find the mass for our block C, we need to use that weight force that we were given, which is that mg, and then divide it by our gravity, because obviously mg over g is going to just leave us with m. So our numerical value for gravity in the English unit system is going to be 32.2 feet per second, I believe, or pounds per second, sorry. So actually it is feet per second squared. So our mg value is 3200. You divide that by our number for gravity, which is 32.2, and that is going to leave you with 99.38 pounds for the mass of our block C. So now, plugging in everything we have here on the bottom, we have our 1/2 times our mass, which is 99.38 pounds, times our velocity, which is 10 feet per second squared, and then that's going to equal our 1/2 k, which is what we need to find, times our delta x max, which in this case is 6 inches. However, since we are using feet in our velocity, on the left side of the equation, I converted the 6 inches to feet on the right side, which is just going to be 1/2 foot. So then throwing everything on one side of the equation, leaving k alone, you have 1/2 99.38 pounds times your 10 feet per second squared. That's going to be over 2, which is just throwing this 1/2 on the other side, times your 0.5 feet squared. The 2 and the 1/2 will cancel, just because you have 1/2, which is divided by 2, so those would cancel. And then what this does, when you calculate that out, you should get a k of around 39,800 pounds per foot. Sorry. So I hope you guys like the video and hope it was useful. And thanks for watching.